Hi. Now we have seen the definition of the Laplace transform. It is an integral expression, but associated with the Laplace transform, we have the concept of region of convergence. The region of convergence of the Laplace transform is determined by the real part of S, namely sigma, okay, and therefore when we calculate the Laplace transform of a signal, we have to calculate the expression in terms of a function of S together with the region of convergence. Now in this video we are going to see that the importance of the region of convergence as follows. We are going to see that two different signals have the same Laplace transform expression, but their region of convergences are different. Okay, different sets on the S-plane. So let us see the calculation of the Laplace transforms of these two signals simultaneously. So on one half, we are going to calculate the Laplace transform of the signal x1 of t, and on the other half, x2 of t. Okay, let x1 of t be equal to e to alpha t u of t. Okay. Now alpha has a real part alpha r, and it has an imaginary part alpha I, is a complex constant. Okay. Now here x2 of t is defined as follows. It is minus e to alpha t u of minus t. Okay. And alpha is again alpha r plus j alpha I. This is the complex constant. And in these signals, alpha is chosen to be the same complex constant. The alphas are equal. That's why we show them in both signals by the same symbol, alpha. Now it is clear that x1 of t is non-zero only for positive values of t, and x2 of t is non-zero for negative values of t. Okay? So x1 of t is therefore right-sided. It's a right-sided signal, and x2 of t is left-sided. When we plot x1 of t or x2 of t, x1 of t will have non-zero values in the graph for positive values of t, therefore it's right-sided, and x2 of t will have non-zero values for negative values of t, therefore it will be left-sided. Now let us calculate the Laplace transform of x1 of t. So x1 of s is from minus infinity to plus infinity, x1 of t e to minus st integrated with respect to t. Similarly, x2 of s is from minus infinity to plus infinity, x2 of t e to minus st integrated with respect to t. Remember, s is the complex variable, sigma, s is sigma plus j omega. Okay? Sigma is the real part of s and omega is the imaginary part of s. Okay, now we know that x1 of t is e to alpha t u of t. Now, because of this u of t, the integral will be from 0 to infinity. So it will be e to alpha t, e to minus st integrated with respect to t. Now here, for the left-sided signal, we have u of minus t. Therefore, the integral will be from minus infinity to 0 of minus e to alpha t e to minus st integrated with respect to t. Now, okay, we have these integral expressions, but we ask the following question: under which condition can we claim that these integrals exist? For example, let us look at the first integral. We have the exponential function e to alpha t times e to minus st. So in fact, we can combine this as a single exponential term, e to alpha minus st integrated with respect to t. Similarly, this one is from minus infinity to 0 minus e to, again, alpha minus st integrated with respect to t. Okay. Now, we know that, for instance, let us look at the first integral. We know that this integral is convergent if, now here we have a complex quantity. S is the variable, alpha is constant. We know that the imaginary part of S or of alpha will play no role in the convergence of this integral. Only the real parts will play a certain role, and we know that this must be a decaying exponential in magnitude. The imaginary parts give rise to sinusoidal expressions, as we remember. So this integral is convergent if real part of alpha minus s is negative. Okay? So this integral exists if real part of alpha minus s is negative, or real part of s is greater than real part of alpha. Or again, in terms of real part of S and real part of alpha, sigma greater than alpha r. Okay. Okay, let me repeat once more. The convergence issue related to this integral is completely related to the real parts of S and alpha, because the imaginary, contributions of the imaginary parts will be just sinusoidal oscillations. They play no role in the convergence of the integral. So for the convergence of the integral, the exponential, we require an exponential decay as t tends to infinity. So that exponential decay is guaranteed if real part of alpha minus s is negative. Or we end up with this condition. Now let us look at the other problem, the left-sided signal. Again, this integral exists if real part of alpha minus s is positive. Why? Because, again, we require an exponential decay as t now tends to minus infinity. As t tends to minus infinity, the real part of alpha minus s must be positive, and therefore, as t tends to minus infinity, we will have exponential decay. Okay? Or real part of s less than real part of alpha, or again sigma less than alpha r. Okay, here sigma is the variable, alpha r is fixed because alpha is the constant. Okay, so how do we calculate the integral? Therefore, x1 of s will be equal to 1 over alpha minus s e to alpha minus st evaluated as 0 and infinity. Now here we know that when t tends to infinity, since the real part of alpha minus s is negative, or we choose sigma such that sigma is greater than alpha r, and this condition is satisfied, as t tends to infinity, we will have 0. So we will have, when t is equal to 0, we have 1 over alpha minus s, but with a minus sign, so we have 1 over s minus alpha. Okay? Now let us look at the other case. x2 of s is equal to minus 1 over alpha minus s e to alpha minus st evaluated at the integration limits. Now again, as t tends to minus infinity, we know that the real part of alpha minus s is positive. Therefore, as t tends to minus infinity, it will decay exponentially and it will decay to 0. So we have the only non-zero contribution is at t equal to 0. At t equal to 0, we have minus 1 over alpha minus s, or 1 over s minus alpha. So we have the same expressions. The Laplace transform of x1 of t is 1 over s minus alpha, and the Laplace transform of x2 of s is also 1 over s minus alpha. So their functional expressions are identical. However, the region of convergence for x1 of s, let us show this ROC1, is all those s such that real part of s is greater than alpha r. Okay? Let me write this over here so that we will have sufficient space. So ROC1 will be equal to all those s such that real part of s is greater than alpha r. And here, similarly, the region of convergence is all those s such that real part of s is equal to sigma, in fact, is less than alpha r. So on the complex plane, if we plot the S-plane, and suppose that this is our alpha, so real part of alpha is alpha r, so this point here is alpha r. The region of convergence is sigma greater than alpha r, or this region, this shaded region. This is the region of convergence for x1 of s. For x2 of s, on the other hand, again we have the complex plane, sigma and j omega, and this is our alpha, which is the complex constant alpha r plus j alpha I. So this point on the real axis is alpha r, and the region of convergence is real part of s, or sigma, less than real part of alpha. So this is our convergence region. Okay? So this is a nice example showing that we may have two completely different signals. For example, here we have a right-sided signal and we have a left-sided signal. Their Laplace transforms turn out to be the same in terms of a function of s, but the region of convergence, or the set of s, the subset of the S-plane, over which the Laplace transform integral converges, that is the region of convergence. The region of convergence for x1 of s and x2 of s are, of course, different. Okay, thanks for watching.